Hello, how we doing? Has anybody tuned in yet? Has anybody tuned in yet? Or am I all alone right now? Nothing yet? Alright, well, I'm just gonna go ahead and start, I guess. Alright. So right about here is the start of geometry notes. Welcome, welcome. Happy Sunday. Happy beginning of a 4-day week. We have a 4-day week this week, right? Because of Nevada Day on Friday. So yeah, we are doing our last lesson of Unit 4. We've been looking at triangles the whole time, right? So this is I'm not saying we're never going to look at triangles again, but this is our last lesson, really focusing on triangles. So today we're looking at mid-segments and medians. So I guess I need to share my screen, don't I? There we go. So we're looking at mid-segments and medians. So, what is a mid-segment? What is a median? Actually, I might restart. I might make a new. If you're watching this replay from the very beginning, I might restart. I always in the description have the little timestamps to when I. So I might restart what I have, because I'm gonna check to see. Yeah, I don't have the module created on Canvas. So I don't have the notes posted. That's my bad. So week 10. I could have sworn I made these. Unit 4. Adding the notes to. I could have sworn. This. I could have sworn I made these modules. All right. So let me go ahead and add that then. So text header, I need to add 4.4. And this would be. Here, I'll just share my screen so you guys can see what I'm doing. Mid segments and medians. That, and then I need to add quotes. So that. emoji. So like 4 printable notes, and then add the assignment. Perfect. Okay, so both of those are posted there now. And then right, we're going to have 4.3 and 4.4 quiz. Prepared yet? Okay, so now those things are posted. So if you guys want to follow along, you can. All right, so right here is the start of the unit for lesson 4 notes. I just posted the notes and the assignment for this live stream, so you can follow along with the 4.4 printable notes. Click on it, right? These are the notes that I am about to do. Boom. So I've got the notes pulled up here, and what we're looking at is mid-segments and medians. So what is a mid-segment? What is a median? Well, let's take a look. So a mid-segment of a triangle is a line segment that connects the midpoints of two sides of the triangle. So D is a midpoint and E is a midpoint, and we're connecting these 2 points together. So that right there is a midsegment. A midsegment of a triangle is parallel to the side that it's not touching. So that is saying that this side, or that segment, and this side that it's not touching are parallel. That's what we're getting at here. So these two lines are parallel. And, well, we have seen parallel lines before, and this is a transversal, right? That's a transversal. So we have some of those angle relationships that we're used to: alternate interior, alternate exterior, those sort of guys, okay? And another fact that's true is a midsegment is half as long as the side that it's not touching. So this segment might be 10, let's say, inches long. Well, the midsegment is always half of that, so therefore that is 5. That's just an example, right? Let's just focus on the midsegments, and then I'll come back to medians. So what we're seeing here, this problem says solve these problems using the fact that these are midsegments. So I'm telling you that this segment right here is a midsegment, and that means that A is a midpoint of RS and C is a midpoint of RT. And what does it mean to be a midpoint? Well, that means that AR and AS are congruent. They're the exact same length. Okay? And if this is also a mid-segment, we already know that A is a midpoint. Well, that means B is a midpoint. If B is a midpoint, well, that means that BS and BT are the same length, because B is in the middle. And BC is a midsegment, right? We were told they're midsegments, okay? Well, that means C is a midpoint, which means that CR and CT are the same as well, because C is in the middle. So we're going to use that to help us solve for some of these questions. the other two facts that we need to know is that the mid segment, right? We already set it up here, but I'm just writing it again so that way we have it right here. The mid segment is parallel, that symbol means parallel, to the side it does not touch. The mid segment is half as long as the side it does not touch. Okay? So these first two questions are referencing this fact, right? So AB is right here. Well, it is parallel to the side it's not touching. It is parallel to RT. ST is this side right here. Well, it is parallel to the mid segment that's not touching it, meaning that orange one right there, which is AC. You see that? So this mid segment is parallel to this one, and this mid segment is parallel to that side, and this mid segment is parallel to that side, right? Because it's touching these two. So it can't be parallel to that. It's parallel to the one that it's not touching. Let's clean this up a little bit. What just happened? Did it just crash? That's a shame. So let's clean this up a little bit. So we're looking at a blank scale or blank page. I'll remark these real quick. Okay. So AC is this side right here. They're telling us it's 10 long. How long is ST? Well, ST is the side that it's not touching. The mid segment is half as long as the side it does not touch. So 10 is half of ST. Well, that means this must be 20. So this whole thing is 20. Take half of that and you get 10, of course, right? SR is 24. Well, take half of that and you get the mid segment. Half of 24 is 12. Therefore, BC is 12. R to C is 4. How long is AB? Well, AB is half of RT. Well, RC is half of RT, right? And here's the other half. It's 4. So the whole thing's 8, but half of that is, of course, 4. So this half is always going to be the same as the mid segment, right? Because it's half the entire side. So the whole side's 8. So half that's simply 4. And the last piece here, if AB is 2x plus 3, how long is RT? 3x plus 7. So we're pretending these numbers don't exist anymore, right? These are separate problems. So this is no longer 4, okay? That was the problem before it. Now we're saying that, oh, RT is 3x plus 7. So AB is half of RT, okay? In other words, if we double 2x plus 3, that should be equal to 3x plus 7, right? Or another way to think of it is it takes not one of these, but 2 of them to make the whole thing, right? So if we add it to itself, it takes two of them added together to give you the whole thing, right? Think of these other examples that we already had, right? If this is 12, 12 plus 12 gives us 24. This is 10. 10 plus 10 gives us 20. Well, this is 2x plus 3. 2x plus 3 plus 2x plus 3 gives us the other side, which is 3x plus 7. So again, 10 plus 10 gives us 20. 12 plus 12 gives us 24. 2x plus 3 plus 2x plus 3 gives us 3x plus 7. I understand that it's not numbers, but it's still the same idea. We're still doing the same thing here. So 4x plus 6 equals 3x plus 7. Subtract the 3x over, you get x, and subtract the 6 over, you get 1. So x is equal to 1. Now, it didn't ask us for x, it asked us for RT. So what do we do with that? We plug it in, and we get 10. By the way, if I were to take 1 and plug it into this guy, 2 times 1 plus 3, I get 5. I guess we did it right, because 5 is half of 10. So it all works out. So that's midsegments, right? We're connecting a midpoint to a midpoint to a midpoint. So those three facts, again, are that number one, these are obviously the midpoints. So this side is congruent to that side, this half is congruent to that half, so on and so forth. And then the two facts that are maybe not as obvious is that, number one, this side is half as long as of the side right there, as well as is parallel. Parallel and half as long. Parallel and half as long. Okay. Now let's take a look at medians. A median of a triangle is a line segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. So if you don't remember what a vertex is these 3 points, the points of the triangle, right? Point J, L, and K are the vertices of the triangle. So where the sides come together. This is a side, and where the sides come together, you have a vertex. So those are vertices, plural. Okay. So we're connecting a vertex to a midpoint. So instead of connecting a midpoint to a midpoint, we're connecting a vertex to a midpoint. And we get 3 lines that look like that. So the 3 medians of a triangle are concurrent. The point of concurrency is called the, I forget what that word is. It's called the centroid of the triangle. Don't worry about that word. Obviously, I forgot what the word was. What does it mean to be concurrent? All 3 lines intersect at the same spot, as you can see here. So no matter what triangle you draw, you could do this at home if you wanted to, right? Draw yourself a random triangle, get a straight edge, and go from vertex to the midpoint. Vertex to the midpoint, vertex. Doesn't matter what triangle you draw, they will always intersect one another at the same spot. That point is called the centroid. And what's mathematically nice about this, what happens to happen, is that the segments end up in a ratio of 2 to 1. Meaning, if you look at these lines, when they intersect, can you see that there's like a short half and a long half? It's not actually cut in half, of course, right? There's a short piece and a long piece. You got a short piece and a long piece. You got a short piece and a long piece. The ratio of those pieces is 2 to 1. So this long piece is always twice as big as the short piece. Sound familiar with mid segments, right? The long side is twice as long as the mid segment. Well, when this intersection occurs, the long piece is twice as large as the short piece. So kind of a similar logic that we're doing here, okay? So let's take a look at this example. I'll go back up to example 2, okay? But I want to look at example 3 first, okay? So I want to jump immediately into that rhythm, okay? So taking a look at this picture, L is the centroid. And so here's all these medians that are intersecting one another. You have the short piece and the long piece. You have the short piece and the long piece. You have the short piece and the long piece, right? So this long piece is twice as big as the short. So if this is 8, this must be 4. If this is 10, this must be 5. Okay? What else do we know? Well, we know that R, Q, and P are midpoints because these medians are formed by connecting the vertex, which is where the sides come together, to the midpoint. So P has to be in the middle. So therefore, PO is also 11. If this is 11, then the other half has to be 11. And then MP is this entire thing, right? Well, we already said that LP is 5. So 10 and 5 make 15. That's pretty straightforward. And then N and Q, well, 8 and 4 added together give us 12. There it is. So I'm not going to lie, I don't really like this over here. That's not really how I think of it with 2/3 and 1/3. I don't really look at it like that, okay? I look at this as, well, this piece is twice as big as this piece. How about I add one other thing here? Well, maybe I shouldn't say I don't like this at all. I shouldn't say that because there is a time when it's useful. Notice here in this example, we totally ignored our Apple Pencil's low. Okay. Notice we totally ignored RO. How about I come in here and tell you something? How about I make something up and I tell you RO is what? What should I say? 18. Okay? RO is 18. How long is RL and how long is LO? So RO is 18 and here's L. So this is the short piece and this is the long piece. We know that the short piece is half the length of the long one. All in all, it has to add up to 18. So where does the third come into play? Well, if the ratio is 2 to 1, right? The ratio is 2 to 1. This is essentially a third of the segment, right? If this piece is right here, let me use a different color. So this piece is half as long as this piece. Well, I could come in here and break this piece up, right? So therefore, all 3 pieces are the same. You with me? So this piece right here is 1/3 of the whole thing. Because there's 1, 2, 3 pieces. This is 1/3 of the whole thing. So therefore, if the whole thing is 18, then the short piece must be 6. Double the short piece to get the long piece and you get 12. 6 plus 12 is 18. You see how that worked out? Let's jump back up to this example and we'll keep talking medians. So this one line is a median, okay? So this is a vertex and this is a midpoint. So we immediately know that this half is the same length as this half. So if we want to solve for x, simply set those two things equal to each other. So x is 7. I would encourage you to plug in 7 just to make sure that we did it right. 2 times 7 is 14, and 14 plus 6 is 20. Plug in 7 here. 5 times 7 is 35, minus 15 is 20. Okay, we did it right? They're both 20 long. We did it correctly. So LJ here is 20 plus 20, which is 40. KJ is simply half, so that's 20. And then now that we know x, we can just go ahead and plug it into LM. X is 7, so 28 plus 3 is 31. And we did it. So both midsegments and medians essentially use the same fact. When you're given this long side, take half of that to get the short one. When you're given the short midsegment, double it to get the long one. When we're looking at medians, if you're given the long portion, take half of it to get the short portion. If you're given the short portion, 4, double it to get the long portion. The only thing that was different with medians, and let me make up another example real quick, because this didn't take very long, right? This was pretty straightforward. Here's a median connected to a midpoint, and here's a median connected to a midpoint. Not really a midpoint there. I didn't do a very good job. Boom. So there's a couple of medians intersecting. If I told you that RT was 21, if I told you RT is equal to 21, how long is NT? Well, again, this short piece is 1/3 of the whole thing, right? Because you could imagine if you can double NT to get RN, or you could think of this as, well, if you were to cut this in half, right? This half and this half, they're all the same length, right? Imagine there was a point right here, right? All three of these are the same length. So there are 3 pieces, 1, 2, 3, that make up the whole thing. So NT is 1/3, because there's 3 pieces, 1/3 of the whole thing. So divide 21 by 3 and you get 7. Double 7 and you get 14. 14 plus 7 is 21. So it works out, right? The short piece is half the length of the long piece. And when you add them together, they end up equaling 21, 14 plus 7, just like we wanted. And let's say UV is, I can make up one more, let's see. I'm trying to make it work out to the pattern, you know what I mean? 36. Let's say it's 36. So I know it's clearly shorter. It's clearly shorter than RT, but I'm not to scale. If UV is 36, well, 1/3 of that, 36 divided by 3, is 12. So the short piece, N to V, must be 12. Double that to get the long piece, you get 24. Does 24 plus 12 equal 36? Indeed it does. The pattern works out. All right, and with that, that's the notes. I would not don't at all worry about these words. They really don't matter. The only word that mattered, I guess I should say, is centroid, right? Centroid is where the medians intersect one another. Centroid is where those medians intersect one another. Um, I would just like there might be one question in the classwork about these guys. Just take a look at this strong. Just take a look at this. I'm not asking you to memorize anything. I'm just asking you to be able to read these words. So, the incenter is the intersection of angle bisectors. We know what angle bisectors are. That's a line that splits an angle in half, of course, right? So when you draw all three of those, they intersect at the same spot. That's a true fact, no matter what triangle you gave me. Centroid is the intersection of medians. We already discussed that. Circumcenter is the intersection of the perpendicular bisectors. So to bisect means to split in half, but specifically a perpendicular, so it's 90 degrees. Those lines will always intersect one another. And this right here is the vertex drawn straight down to the opposite side, making a right angle. Similar to median, except a median goes to the midpoint, where this isn't going to the middle. It's just going straight down. Right? The median would look something like that, right? Now that's half and half. So the median isn't straight down, whereas this line is. I'm not really asking you to memorize those. I'm just asking you to be able to look at this picture and to somewhat just kind of see. I just want you to realize that triangles are kind of cool and special, and all these lines intersect each other for any triangle. It's kind of crazy. For any triangle you ever drew, the angle bisectors will always intersect. The perpendicular bisectors will always intersect. It's just one of those things. It's kind of crazy. All right. So with that being said, that's our mid segments and medians. Pretty straightforward today. I'm feeling pretty confident that we'll do well on the classwork. It's the very last lesson. I think the quiz will be pretty easy. So yeah. So thank you for watching live. If you're here, no one messaged in the chat, so I have a feeling there's not really anyone here. That's okay though. So hopefully we watched the replay, and thank you for watching the replay if you're still listening to me. So with that being said, I'm going to make an announcement for I'm going to make an announcement for Algebra 2. So courses, Algebra 2. I'll go ahead and I can share my screen. I don't really care. So yeah, I'm going to make an announcement for Algebra 2. Going live on Twitch for lesson 4.1. Starting Unit 4. Make sure to watch the replay if you miss out on the live stream. Four-day week this week. And all classwork is due at the end of the week for Unit 3. Sure to keep that in mind. See you in the chat shortly. I'll take out the word shortly. See you in the chat. Link. Or make sure to watch the Blue 4-day week this week. And I'm going to publish this module. Notes in the live stream are good to go. Hold on. All right. Pull up the notes here. Any Algebra 2 folks out there yet? Hello, Joy. Or J-O. Urbano. How you doing this afternoon? Having a good weekend so far? Good. Glad to hear it. We'll give it another minute or two to maybe have a couple more of us join. All right, so I guess we'll go ahead and jump in. So we're looking at nth roots. So we're introducing the idea of more than just a square root. We're introducing the idea of a cube root, a fourth root, a fifth root, a sixth root, all of these things. Okay. So we are. This is a nice little breakdown of roots and whatnot. Let's remind ourselves of which, by the way, okay, right here is the start of 4.1. So I can mark that. So we're used to square roots. We know that the square root of 4 is 2. We know the square root of 9 is 3. Why is that, right? Well, the square root, we're looking for a number that when you multiply it by itself, right, it gives you 9. So the square root of 9 is 3 because 3 times 3 is 9, right? And the square root of 16 is 4 because 4 times 4 gives you 16. Well, what does it mean to have the cube root of something? Well, Now instead of a number times itself, it's a number times a number times a number, 3 times now. So the cube root of 8 is 2, because 2 times 2 times 2 is 8. It took 3 2's this time instead of 2. So the square root of 4 is like groups of 2, because it's a square root. So you're looking for groups of 2. So 2 times 2 gives me 4. So the square root of 4 is 2. But the cube root of 8 is 2 as well, because 2 times 2 times 2 is 8. The cube root of 27 is 3, because it takes 3 3's to give me 27. The cube root of 64 is 4, because it takes 4 4's. Okay. The square root of 16 is 4, because it only takes 2 4's to give me 16. But the cube root of 64 is also 4, because it takes 3 4's, right? So cube root is groups of 3. I'm sure you can guess with a fourth root, it's groups of 4. So the fourth root, so the square root of 16 is 4. What's the fourth root of 16? 2, because it takes 4 2's to give me 16. We'll keep looking at this, but that's just a quick teaser as to what we're looking at with roots. Square root, groups of 2. Cube roots, groups of 3. Fourth roots, groups of 4. Fifth roots, groups of 5, so on and so forth. So, first, let's start with this idea of rewriting an expression. Okay? We are rewriting our expression. So we are taking this thing that looks like a radical and going, or not looks like, it is. It's got this radical. That's what this symbol is called, right? This is a radical, okay? So we're going to rewrite this thing that has a radical and rewrite it with an exponent. Okay, so we're rewriting this thing with a radical with an exponent. So take a look at these examples up here. You can rewrite a root using a fractional exponent. You can rewrite a root with a fractional exponent. And I understand that this is new and different and you've probably never seen it before. And it doesn't have to make sense right this second. Like, it might seem like, well, that seems kind of random. I would agree. That does feel kind of random. But it works. And we just need to catch on to the pattern. We just need to catch on to the pattern, okay? I'm not asking you to understand it to its full extent. I'm just asking you to catch on to the pattern. So this cube root gets rewritten as 7 to the 1/3. So the size of the root is the denominator. You see that? And if you've got your notes printed, right, taking a look at this right here, the size of the root becomes the denominator. The size of the root is the denominator. So if I were to do this several more times, you have here, this becomes 12 to the 10/6. So the exponent that we just had goes to the numerator, and the size of the root is the denominator. You see that? It might seem weird or random, as I already said. I'm not asking you to understand why it is that we're writing it this way. You don't need to understand that right this second. What you just need to understand is the pattern. So the exponent went to the numerator, and the size of the root went to the denominator. So how do we rewrite this? 11 to the, well, that's not all. 11 to the exponent goes to the numerator, and the size of the root goes to the denominator. You might be thinking to yourself, well, there's no number there. What number is hidden for a square root? It is a 2. It's a 2. Remember, because we were looking for groups of 2 for a square root? So it's a 2 that we can't see there, okay? And last but not least here, negative 42 raised to the exponent goes to the numerator, and the size of the root is the denominator. All right, that's the pattern. The exponent here, the 2, goes to the numerator, the top of the fraction, and the size of the root goes to the denominator, the bottom of the fraction. So that's the pattern. And again, I just want you to catch on to that pattern. So now let's go in the opposite direction. So when you see something that's 19 to the 1/3 power, that's how I read this. This is 19 being raised to the 1/3 power, right? It's not as easy to say. It's not like 19 squared or 19 cubed. It's not quite that easy to say, right? It's a little bit more of a mouthful. So 19 being raised to the 1/3 power. Okay. Well, what do we know? The denominator, the bottom of the fraction, is the size of the root, and the numerator is the exponent. Well, we never write 19 to the 1. Nobody ever says that. So it's simply the cube root of 19. The denominator is the size of the root. So this is a square root. We never really write the 2 for square roots, okay? And then inside is 7 cubed. And this one here, the denominator is the size of the root, and the 2 is the exponent, just like so. This is the size of the root, 7th root, kind of weird, right? And then 14 cubed, right? That's the exponent. Some students have asked me in the past, like, how do I know whether the exponent goes on the inside or the outside? And my answer to that is, it doesn't matter. It does not matter. I could have chosen to write this like this. These two things are the same. They have the same value. If you could plug that into a calculator, which I understand you might not know how to punch that into a calculator right now, but if you did, you'd get the same answer. So it's just another way of writing it. So to recap here, looking at this pattern, right? A radical can be rewritten with an exponent. And something with a fractional exponent can be rewritten with a radical. Okay? That's what we just learned in that moment. The size of the root is the denominator, and the numerator becomes the exponent when you write it as a radical, right? That's the back and forth there. Okay? We're going to keep using that, okay? So it's not going to disappear. I'm not just moving on. We're going to keep kind of thinking about that in the back of our head. So, evaluate each expression without using a calculator. So 8 to the 4/3. What is that? Well, it might help you to think about it if you rewrote it using the radical notation. So what do we know? 3 is the size of the root. So we're taking the cube root of 8. And 4 becomes the exponent. Remember, I can write it like this or like this. It doesn't matter which way you do it. It really doesn't, okay? It does not matter which way you do it here. So, which would you rather do? What is 8 to the 4th, by the way, if I plug that into a calculator? 8 raised to the 4th power. Would you rather take the cube root of 4096? Or would you rather take the cube root of 8 and then raise it to the 4th power? I don't know about you, but I'd rather just simply take the cube root of 8 and then raise it to the fourth power, as opposed to asking myself, what's the cube root of 4096? You see my logic on that? So we're going to do the inside part first. What is the cube root of 8? I've already told you that answer. It's 2. Why? Because 2 times 2 times 2 gives me 8. It takes 3 2's in order to give me 8. Square root is groups of 2. Cube root is groups of 8. Or cube roots is groups of 3. So the cube root of 8 is 2. And then we're going to raise 2 to the fourth power. You can do that in your head, you can do it on your fingers, or you can do it in a calculator. 2 to the fourth is 16. So the final answer is 16. See what I did there? Take a look at this next one, right? Do the inside part first. What's the fourth root of 16? Well, it takes 4 2's to make 16. So the fourth root of 16 is 2. And then 2 cubed, 2 times 2 times 2 is 8. Let me show you something here. Table of roots, or table of powers, sorry. Table of powers. If you Google table of powers, one of the very first Google image searches or images on the search is this guy right here. 1 to the 1 power is 1. 1 squared is 1. 1 cubed is 1. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. 3 cubed is 27. 3 to the fourth is 81. You can also go backwards, right? The cube root of 8 is 2. The fourth root of 16 is 2. The square root of 4 is 2. The square root of 16 is 4. The cube root of 64 is 4. You can go back and forth. So 4 cubed is 64, and the cube root of 64 is 4. You see how I'm using this table? So what's our next question? 32. As the numbers get weirder and stranger, you might not know what the fifth root of 32 is. You might not know, all right? I encourage you to look at this table and find the number 32. The fifth root of 32 is 2. This is our first time seeing a negative exponent. That's something I kind of grazed over from the beginning here. A negative exponent tells you to take the reciprocal. Take the reciprocal. Let me give you some quick hot examples here, some real quick ones. What's 2 squared? That's 4. What's 2 to the negative 2? That's 1/4. What's 3 cubed? That's 27. What's 3 to the negative 3? That's 1 over 27. Taking the reciprocal, just simply flipping it. Okay? So when I look at this, what's 2 squared? That's 4. What's 2 to the negative 2? 1/4. Two squared is 4, versus 2 to the negative 2 is 1/4. Okay? And last but not least, what's the fifth root of 1024? That's where my table really comes in handy. Do you see the number 1024? It's right there. The fifth root of 1024 is 4. I would not expect you to just know that off the top of your head. This table is very helpful, and I'll probably post this on Canvas so that way we don't have to go searching for it every single time. I'll just post the picture. But for now, that's what I Google searched was table of powers. It's the very first thing that comes up. So the fifth root of 1024 is 4. There it is. To keep it going, the cubed root of -8 raised to the 5th power, right? So eventually you're going to get some of these memorized if you haven't already. The cubed root of 8 is 2. The cubed root of -8 is -2. Not 2i. You can't take the square root of a negative number, but you can take the cube root of a negative number. Why is that? Well, if you go to a calculator, right? -2 times -2 times -2. So I do it 3 times. The negative times a negative will cancel, but times it by the negative again, and you get -8. You can't take the square root of a negative number because when you multiply two numbers together, how would you ever get a negative, right? A positive times a positive is positive, and a negative times a negative is positive. How would you ever get a negative? You won't. Hence, it's imaginary. But you can take the cube root of a negative number, because when you do a number that's negative, when you do it 3 times, the first 2 cancels out the negative, but the third time brings back the negative. So you can take the cube root. That is actually okay. So I end up with the cube root of -8 is -2, and then raised to the 5th power. If you don't know what 2 to the 5th is off the top of your head, you could still use the table. 2 to the 5th power is 32. So I end up with -32 because of the negative. Okay. Something worth noting, the odd root of negative numbers is negative. Right? When I take an odd root, 3 is an odd number, of a negative number, the answer is negative. Also, when I raise a negative number to an odd power, the answer is negative, right? So -2 squared, for example, is +4 because -2 times -2 cancels. But when I do a negative 5 different times, well, the first 2 cancel, and the second 2 cancel. So that becomes +4. That becomes +4. 4 times 4 is 16. But the second you do that last one, +16 times -2 gives me -32. The 5th root of 243. I don't know what that is. Do you? The 5th root of 243 is 3. Three to the 6th is 3 to the 6th. 3 to the 6th is 729. But that negative's on the outside, so it makes it -729. Notice the difference between the negative here and here. All right, the negative was included, whereas the negative is after the fact. 3 to the 6th is +729, but then the negative is applied afterwards on the outside, so it's -729. The parenthesis matters there. Had I had that would be +729, because that's an even number, right? So the negatives would cancel. But this negative is on the outside, so it's not included with the exponent, right? It's something that's after the fact. Same thing is happening here, right? This would be written as the square root of 4 to the 5th, like that, right? That negative is not attached to the 4. It's on the outside. So the square root of 4 is 2. 2 to the 5th is 32. So in the end, I have -32. This last one, we have a negative root, which is kind of weird. But what is a root? That is the same thing as writing -1/4, right? The size of the the size of the root becomes the denominator. Okay, and what did I say about negative exponents? It means to flip your answer in the end. So let's pretend that that's not a negative for just a hot sec, and just do the 4th root of 81 over 1296. You can split that up to look like this if you want. Okay, you're able to split up. You don't have to do it like all at once per se, right? You can think of them as two separate problems if you'd like. So the 4th root of 81 is 3. And the 4th root of 1296 is 6. That simplifies down to 1/2. And what does the negative mean? It actually meant to flip our answer. So in the end, we get 2. Right? I pretended as if it wasn't negative just to not blow your mind for a second and just do the 4th root, right? Use the table, 4th root of, and you get this fraction, 1/2. Well, the negative actually means to flip it, so we get 2. I hope you find that table very useful. I know I do personally, right? Let's look at that table one more time, right? No matter what problem you're handed, whether, I don't care how weird of a root, 5th root, 6th root, 7th root, 8th root, you're handed a problem, and you go, all right, I'm going to take the square root of, I'm going to take the 5th root of, I'm going to take the 4th root of. All you got to do is look at this and go, the 5th root of, find the number. The 6th root of, find the number. Right? That's all you got to do. And then the answer is right over here. So the 6th root of that obnoxious number, 15,625, is 5. The 7th root of 2187 is 3. So on and so forth. All right, let's take a look at these problems that we're solving here. Let's make some use of these roots that we're learning. So compare this problem to 3x squared plus 2 equals 5, okay? Let's compare and contrast. So how would we do this problem? We'd subtract the 2. We get 3. We divide the 3. We get x squared equals 1. And then we take the square root to cancel that. Whatever you do to one side, you do the other. And you end up with plus or minus 1. All right. Compare that to this problem here. 3x to the 4th equals 3. Divide by 3. And you get x to the 4th, which is 1. Well, we're going to take the 4th root of, oh, I don't know what happened there, to cancel. The 4th root of 1 is 1. And if you don't believe me, right, you can look up the 4th root of 1 is 1. Lol. And again, it would actually be plus or minus 1. But it'd still be plus or minus 1. Let's do it again. Taking a look at this problem here, right? Immediately, how do we get rid of this power? We should take the 6th root. Right? Because the 6th root will cancel out that 6, and then we're left with something pretty simple. And when you take the 6th root of 729, you end up with 3. The 6th root of 729 is 3. Obviously, these problems are rigged to come out nice, right? Like, They're on this table, right? What's the sixth root of 728? I ain't got no clue, right? It's a decimal. It's something weird, right? You can plug in the square root of 5 and it's going to be some obnoxious decimal, right? There's clearly decimal answers out there in the world, right? Dealing with some nice numbers for now, okay? So the answer to that is 3. Add the 7. You get 2x equals 10. X equals 5. So x equals 5. Oh, shoot. I messed something up. When we take the root, sorry. When we take the root of something, right, it's always plus or minus. That's right. So we have two equations. 2x minus 7 equals 3, and 2x minus 7 equals negative 3. So we end up with 5. Add the 7, you get 4. Divide the 2, you get 2. And 2. So, I mean, as I was trying to show you here, these problems are no different than what we're used to. It's just that now we're using like a weird size root. Okay. So there's nothing particularly different about how we go about solving, right? What did I used to say? I used to say get the squared thing on its own, right? You want to isolate this term, right? So that way you can just take the square root of it. Well, you want to isolate the x to the fourth, so that way you can just take the fourth root of it now, right? How do you cancel out a squared? You take the square root. How do you cancel out a fourth? You take the fourth root. All right, we have some more. Oh, there's so many examples here. We probably don't really need to do all of these examples, but we have some more property stuff with exponents. Today's just like lots of property stuff. So we already saw this, if you want to call it, property, about how we can rewrite this root into an exponent, or the other way around, how to turn the exponent, right? That's what the little number's called, right? The little 3/2, that's an exponent, right? The number in the top, right? So we took this exponential form, as we like to say, and turned it into radical form because it has the radical, okay? You can go back and forth. So what we're focusing on here is now we're doing a deep dive on exponents. So let's begin to understand exponents, right? We know how to turn a radical into an exponent, but once it's an exponent, what should we do with that? You know what I'm saying? So we're gonna learn some exponential properties. So there's a whole bunch here, and I would encourage you to have this handy while you do the classwork. I would encourage this to have it handy while you do the classwork. So this is saying, notice all of these all have the same base, right? It's the same number. The big number, right? 3, 3, 3, 4, 4, 4. The big number is the same. So when that big number is the same, we can simply add the exponents together when we multiply. So that's what this property says right here. So this number is the same, so we can simply add the exponents. So we get 25, because 6 divided by 3 is 2, 5 squared is 25. So basically, why are we doing this is because something messy, something that looks pretty kind of gross and ugly with like these fractional exponents, and it's like a little intimidating, right? In the end, the answer is just 25. So when you multiply two things together that have the same base, you can just add the exponents together. Okay. All right, well, what if we have an exponent raised to an exponent? Well, that's what this property says here. When we have an exponent raised to an exponent, we are multiplying those exponents together. So let's think of this, right? Let's see if you see the kind of the pattern, right? So when you multiply things together, all you do is add, and when you do an exponent to an exponent, all you do is multiply. It's kind of like a notch down, right? If I were to think about like growth, how do you make things bigger? You can add numbers, you can multiply, or you can raise it to exponents, right? To add to is kind of mediocre. To multiply by 2, it doubles it. To square something makes it even bigger. 5 plus 2 is 7. 5 times 2 is 10. 5 squared is 25, right? It's like we're up a notch, right? So multiplying, all you do is add one notch below. Exponents, you multiply them. So all this to say, 7 to the 2/3 raised to the 5 halves is the same thing as 2/3 times 5 halves. So we multiply the exponents. So 2 times 5 is 10. 3 times 2 is 6. So 7 to the 10/6. We can reduce that fraction. 10 and 6 are both divisible by 2, so we end up with 5/3. How can we combine these together? Well, they're the same size root. So we can, because they're the same size root, we can just combine the insides. So that's the 4th root of 12. So that's not actually listed here, but I think it's listed up above. No, it's not. Okay. Well, I can just write something, when we have the same size root, just multiply the insides. Taking a look at this, all we're trying to do is simplify. So the 4th root of 240 over 15. So we can actually reduce 240 over 15, right? 240 and 15 are both divisible by 15, right? 240 divided by 15 is actually just 16. So actually, this is the 4th root of 16. And what's the 4th root of 16? 2. And if you don't remember that, I can show you on the table here. The 4th root of 16 is 2. Again, how do we handle an exponent to an exponent? We multiply. I'm not going to lie, the list of properties is not the shortest in the world, but if you do enough, if you look at these examples and you look at this property table while doing the classwork, it's not like we're doing something particularly difficult. It's just, I don't want you to think it's difficult. You just got to know which property to use. And hopefully you see the distinction between this problem and this problem, right? This is multiplying two things together. This is an exponent raised to another exponent, right? So we multiply those exponents together and we end up with 10 to the 2/6, which reduces down to 10 to the 1/3. The 1/3 exponent, well, remember, that's the same thing as a cube root, right? To have 64 to the 1/3 is the same thing as a cube root of 64. We need to keep that in the back of our mind, right? Whenever you see a fractional exponent, you got to also be thinking like, is there any way I can like take the cube root of this or something like that? So I'm inclined to take a look at this. The cube root of 64 is 4. And that other number on the screen there was 125. The cube root of 125, is 5. So this just simply breaks down to 3/5. If multiplying means you add the exponents, then dividing means you should subtract. All right? Up here, we did 5 to the 2/3 times 5 to the 1/3, or 4/3, sorry, and we added them together. That was for multiply. Well, now if we're going to divide, a fraction is division, right? If we're going to divide, we should subtract. And there's a perfect example right here, right? If we're going to divide two things, then you subtract the exponents. So 10 to the 5/6 minus 4/6 is 10 to the 1/6. Again, we have the same size root. So all you got to do is multiply the insides together, and you get the cube root of 8. Well, wait a second. The cube root of 8 is just 2. So that's actually my final answer, right? We want to simplify this as far as possible. All right. Last one of these few here. Oh, I guess we got a few more. There's so many examples. We better all be good at this by the time we're done. So there's a lot of properties happening here, right? We've got multiplication, and we have an exponent raised to an exponent. Let's do, please excuse my dear Aunt Sally, right? We got to do the exponents first. Exponents comes before multiplication. So I'm going to do this in 2 steps. When we have an exponent raised to an exponent, what do we do to combine them? We multiply, right? I have the properties memorized, right? Again, I saw your channel. Can't make any promises. Yeah, I'll hope. When we multiply, again, what I like to think of it as like a notch down. Isn't F supposed to be 4/5? Oh, sorry, I missed that, chat. Yes, it is. Yeah. This was 4. The cube root of 64 is 4. You're right. I saw it on the table, but then, yeah. My bad that I missed that one. Did I miss that, chat? So the properties here, the way I like to think of it is, like I was saying, like when you add something, you make it a little bit bigger. When you multiply by something, you're making it somewhat bigger, and when you raise it to an exponent, you're making it like quite a bit bigger, right? I kind of think of these as like a tier list, right? And the example I used was 5 plus 2 is 7, 5 times 2 is 10, and 5 squared is 25. So there's like this tier list. Well, when you're looking at these properties, it's like a tier below. So when I multiply two things together that have the same base, I simply add the exponents. It's a tier below. So when I have an exponent raised to an exponent, I multiply them together. That's a tier below. And then you can think of it the other way around for these properties, right? When I have when I divide something, a tier below division is subtracting, right? So that's why I'm subtracting the exponents on that one. This one might seem kind of random. A negative exponent means to flip it. So, yeah. So when I look at this, I have an exponent raised to an exponent. How do we combine them? By multiplying. So 2 to the 6th times 2 times 4 is 8. Now I have the same base and I'm multiplying them together. Well, if I'm multiplying, all I do is add the exponents. We're so close to being done. How can I rewrite this as a fraction, as a fractional exponent? Remember, from at the very beginning, this is the same thing as the size of the root becomes the denominator, the bottom of the fraction, and the exponent becomes the numerator. Well, 14 over 7, that's just 2. So 2 squared is 4. This whole thing simply equals 4. Let's just keep going at it. So this is a situation. So increased difficulty. So we're increasing the difficulty just a little bit here. When you look at this table, what is the cube root of 32? Not on here. It doesn't come out clean and pretty. The fifth root of 32 is 2. So there's 32. But this is asking us to find the cube root of 32. Okay? It's asking us to find the cube root of 32. Well, so you remember how when you take the square root of 8, that's not a square. When you take the square root of 8, what's the square root of 8? Well, we don't know. Right? But do you remember how we were saying, like, okay, find the biggest perfect square inside of 8? That's 4, because it's 4 times 2. I can take the square root of 4, and I have 2. But I can't take the square root of 2, so I have 2 root 2. The square root of 8 is equal to 2 root 2. You remember doing this? Right? We've done it a couple times in here, and you definitely did it in Algebra 1. Another example, the square root of 27. 27 is 9 times 3. I can take the square root of 9. That's just 3. But I can't take the square root of 3. So it's 3 root 3. All right. Well, I'm not looking for the biggest perfect square. I'm looking for the biggest cube that works. All right. So what are my cubes? 1, 8, 27, 64. 32 is divisible by what? Which one of these numbers? 32 is divisible by which one of these numbers? 8. The cube root of 8 is 2, but I can't take the cube root of 4. 2 cube root 4. So it's similar, right? It's similar. We're practicing that idea again. There's 96. 96 is divisible. So it's a 4th root too, by the way. It's a 4th root. Which one of these numbers goes into 96? Well, 250s, all these way down here are way too big, right? So I have very limited options. Is it divisible by 16 or 81? Well, I have a feeling that you have a feeling that it's probably not divisible by 81 because 81 is so freaking big, right? 96, though, is divisible by 16. It's 16 times 6. The fourth root of 16 is 2, but I can't take the fourth root of 6. It's 2 fourth root of 6. Introducing a variable, I can take the square root of 3, or 9, which is 3, and I can take, and what happens when I take the square root of x squared? They cancel, right? And I'm just left with x, so this is 3x. Another way to think of this, I don't mean to like make it more difficult, but I just want to introduce the idea. When you're looking at this x squared, recall, right? How can I rewrite this? That's the same thing as x to the size of the root becomes the denominator, and the exponent becomes the numerator. 2 over 2 is just 1. Hence, why there's just the one lonesome x that comes out. Keep that in mind. Take a look at this, right? Can I take the cube root of 2? No, of course not, right? It's just 2, right? There's nothing that goes into 2 at all. 2 is like one of the smallest numbers ever. But what's the cube root of x cubed? Just an x. So x, let me write this a little bit better. X comes out on the outside, and then the cube root of 2 stays right there on the inside. 3 divided by 3, it's just division. 3 divided by 3 is 1. That's why 1x comes out. What's the fourth root of 16? Right? Because that lonesome 4 means the fourth root, right? That's the size of the root. The fourth root of 16, if you've forgotten, the fourth root of 16 is 2. I'm using this table a lot. Using this table quite a bit. So the fourth root of 16 is 2, but I can't do anything to the x, right? The x still keeps the 1/4. The x still keeps the 1/4, right? Because there's a 1 right here, right? 1, there's no, like, you see how this is like, there's 3 x's. So 3 divided by 3, becomes 1. Well, 1 divided by 3, there's not a group of 3, right? There's only 1 x, right? If I only had 1 x in this problem, right? I have to have groups of 3. That's the big deal, right? For cube roots, I need groups of 3. For fourth roots, I need groups of 4. Well, this fourth root, I would need 4 x's to yank out an x, right? There's only 1, so it's not on its own, right? It's gonna keep the exponent. What's the fifth root of 243? Is that on our list? Indeed it is. The fifth root of 243 is 3. So a 3 pops out, and then what's 10 divided by 5? 2. So 3x squared. All I'm doing quickly is division, because remember, what I'm imagining in my head is that, oh, this is the same thing as 243 to the 5th times x to the 10 over 5, right? So this is 240. There's a 1 that I can't see here on the 243, right? So I'm like rewriting in my head like nonstop, right? The exponent becomes the numerator, and the size of the root is the denominator. So the fifth root of 243 is, boom, 3. And then 10 over 5 is 2. This is much prettier and cleaner. Oh, my pencil just died. With only 3 examples left, my pencil just died. No. I'm going to charge my pencil in the iPad real quick. The few of you that are watching, do you have a question that I could answer? I'm going to give it some quick juice. Do you have a question that I could answer? Rip indeed. It's actually crazy how quickly the Apple Pencil charges. So it'll be ready in like 2 seconds with like 10% battery. No questions for me at all? Look at that. Just like that, we're back in action. All right, last 3. So this is where it all comes together. Can we take the 4th root of 256? Indeed, we can. The 4th root of 256 is 4. Oh, yeah. These are problems that you can do like a million of, and it only takes like 20 seconds. Sort of. Right. Let's get better and better and better. So the 4th root of 256 is 4. And again, I'm thinking like groups of 4, right? I'm dividing by 4. Will it come out clean, right? Like, can I take in groups of 4? So there 4 times 4 times 4 times 4. There's 4 4s. That makes 256. So I can yank that out. The 4th root of 256 is 4. I have a single x. I don't have enough x's to yank anything out. So that's going to stay under the root. And then 4 divided by 4 is 1. So a single y comes out. If you want to imagine it, you can look at it like this, right? So this comes out clean to 4. This comes out clean to a single y. But this doesn't come out clean, as I like to say, right? I'm still left with this fraction, 1/4. There's nothing. Now you might be saying, well, we had 1/4 there. Well, yeah, but that's because I know the 4th root of 256 is 4. But I can't find x on the table, right? So I hope you see the difference there. Here's this one, right? There's 3 x's. There's not enough. You need 4. So that's going to stay inside. There's 5 y's. So there's 4, but then there's 1 left over. So yeah, y is going to pop out, but it's not going to disappear completely. You took one group of 4. However, there was 1 left over on the inside. 8 divided by 4, there's 8 z's. You took 2 groups out. So there's z squared, and then there's none left over, right? So boom, that's it. And then the last one, here we go. So we have an exponent raised to an exponent. Don't forget this 2 here as well. It's getting cubed as well. So, but do you notice? These are the same. Those are the same. When they're the same, it's as simple as adding. So when they're the same, it's as simple as adding. 3 plus 7 is 10. 10 is divisible by 5. So you could imagine rewriting this as 2x squared to the 10 fifths power. Well, 10 divided by 5 is 2. Now all we got to do is square this. That's a lot easier than cubing and taking it to the 7th power. That actually would have been pretty annoying had I done it that way. So we did it this way. And 2 squared is 4. X squared squared is x to the 4th. And we did it. So before I leave you here, do we have a question that we'd like to ask? I know I just asked that, but just in case before we end things here, anything we want to bring up real quick at all? You too. Have a good rest of your day. I'm glad we could do this together. I will see you later. Adios.